Okay, welcome back to 240, everybody. We're going to continue our lecture on output stages today, and I think when we finish output stages, you could say that we've covered kind of the fundamentals of this course. Fundamental principles. How do you get gain? How do you get good noise performance? How do you get good swing? Dynamic range. How do you make things fast? Settling time. Those are kind of the core topics of the course. And then after that, we're going to look at some applications. So we're going to look at some specific building blocks and how you would design them with these considerations in mind. And of course, it's just a teaser. Really, the follow-on course is 247, where you go into detail and design high-speed, high-performance analog building blocks, or into a course like 242, where you focus on RF building blocks. Okay, any questions or comments? If you're wondering where you should be in this course, again, I just want to reemphasize the midterm is kind of the core material you need to know. So if you didn't do well on the midterm, really go through it, the questions that you missed, redo them, come to office hours, discuss them if something's not obvious to you. You should get to a level of mastery where you can just do the midterm without thinking. You just say, yeah, of course, this is that, and if you're at that level already, then you're in really good shape. If not, I think you still have some time to pick up those fundamental skills. If you're the kind of person who learns by application, then really the next few lectures should give you a chance to see those skills in action, and then you might actually learn, if that's the way you prefer to learn. Also, you really should be working on your project. If you did the last homework, that's really a way to get you started, and you probably start out with something fairly standard. You might try something like a telescopic amplifier or folded cascode. Use that as your starting point. See what kind of performance you can get, and then build on top of that. But definitely start your projects. Okay? Questions or comments? Okay, so let's do a recap of last lecture. Last lecture we were looking at Class AB output stages. Everybody likes these pens. So what are the advantages of Class AB over, let's say, a Class A output stage? Just a quick recap to get you guys thinking of where we left off. How about David in the back? So what are the advantages of Class AB over Class A output stages?
You don't have static current consumption?
Yeah, so we don't have no static current consumption, which means lower power. What are some other advantages? There's also no real limit to the output power, right? So output current can be very high. In other words, if we designed an output stage that's Class A, the peak current that we could get out of it was the bias current. Here, the peak current we can get out is really how much voltage we can deliver to the device. Obviously, the supply voltage is going to be a limitation. And one of the output stages that we looked at was basically two followers. And we biased these guys with enough voltage so that there is, let's say, a trickle of current flowing through here to put these VBEs kind of close to, they're both on, so there is some current going through here. But the current, let's say IDC, is going to be much less than the output current you need to drive your load. and maybe we can drive this stage with maybe another follower like this. So so really this is just a series of voltage followers, right? So the input voltage goes here and then it goes to the output, and depending on if it's positive or negative, so if it's a positive voltage, this device tends to turn on and supply current to the load. If it's negative, this device tends to turn on and it pulls current away from our load. This is also very fast because they're just followers, right? The C-in is bootstrapped. And by that I mean that the voltage across this capacitance is nearly zero, right? If this is a perfect follower. And so very little current flows through that capacitor. So this is a very high speed stage. So let's see how we would implement this in CMOS. You know, circuit design, anytime there's a new technology out, the first thing that happens is people go and copy the same circuits from the old technology into the new technology, right? So if you go look at vacuum tube circuits, you find all these amplifier configurations and people just copied them over to bipolar design. So you say, well, where's the creativity in that, right? You know, it's the same exact topology. Well, then when you do that, you find that it doesn't quite work as well as you had hoped because the devices behave differently, and then you have to come up with some innovation. So if we do the same thing with CMOS devices, let's say this is kind of the class B output stage that we might use. And again, it's the exact same circuit. It's a follower driving a resistive load, low voltage gain, high speed. For positive input, this device delivers current. For negative input, this device sinks current. And I think everybody knows the problem with this device is limited swing. Because why is it that in bipolar I wasn't concerned with the swing, but now I am concerned with the swing? Anybody? Well, it's the threshold voltage of these devices, right? So if these were 0 VT devices, I would have good swing. But unfortunately, since VT is bigger than 0, that ultimately limits my swing. Even if I put a full VDD here, right, I still have to drop a VGS here. And even if I take this device so its overdrive voltage is very small, I still have a VT in my VGS. And so here, VDD, this over here can't go much lower, much higher than a VT below VDD. Also, this has the same problem as the bipolar counterpart in that these devices only turn on when the input is sufficiently large, right? And so there's an easy fix to that is to make it a class AB stage. In other words, we're going to connect a little battery here. So this battery sees a total of 2 VGS across it, right? VGS-N plus VGS-P. And that runs against some trickle current, and then the actual load current can go much higher. That's why it's a class AB stage, is if I make the input larger or smaller, then this device basically is going to, if I make the input much larger, then the VGS of this device can be sufficiently large to turn it on even harder and deliver more current, and so on and so forth. Okay, so how am I going to implement this battery in MOS technology? Can we do the same thing we did with bipolars? Stick a couple diodes in there. Yeah, sure, why not, right? Except we could use MOS diodes, right? So here's a diode connected transistor. Here's another diode connected transistor. Let me bias them up with some current. And maybe I drive my output through this transistor here. So so again, by appropriately sizing these devices, I can take this trickle current, mirror it to the output with some, appropriate magnitude, and again, it's a class AB stage. I can now increase and decrease the voltage across these transistors in order to deliver current to the load or push current out of the load. Okay, but again, it has the same problems that we discussed before. Namely, the swing is not so good. Okay. Well, what's the solution for swing in CMOS technology? What's the device that has the best swing? What configuration has the best swing? Yeah, I heard you say common source, right? So let's actually, why not just take something that's very natural in CMOS? Take an inverter. And use it as an output stage. Right? Now I can swing all the way up to a VD-SAT away from supply, above and below. And so what are some of the issues with this as an output stage? Anybody? Say you want to use this for your project. Let's say I add a bonus to the project. Put an output stage and drive a 1 kilo ohm load. Would you use this? Okay, maybe we get somebody else. Anybody else? Just give me one potential issue with this as an output stage. You don't have to give me all the reasons. Just one issue. Yes, Vincent.
The DC bias point?
Yeah, very good. So how do we bias it? And we'll come back to this. The issue is, of course, if we look at the input-output transfer characteristic, it's an inverter, right? So it looks like this. This is V in, this is V out. We want to use it over here where we've got some gain, but how do we design it so the bias point at the input is exactly here? Well, we could set up a current mirror and bias it up to do that, but there's some issues with that. That makes things a little bit more complicated. First of all, how do I avoid my signal current from going into the mirror? In other words, how do I isolate my mirror? So here's my mirror, and this, let's say, is designed to put this at the right current level. Well, I have to also do it for the PMOS device, right? So they're actually shorted together. So I have to make sure this is the right level for both the input and for the top transistor and the bottom transistor. Let's say I've done that. Now if I apply an input signal, I have a diode here, right, to ground low impedance, and now it's going to be hard to drive the stage. What are some other issues? Well, we'll come back to this biasing issue and address it. So think to yourself, what do I like from an output stage? So let's call this a minus. Let's call this a plus, that it has good swing. Okay.
High output resistance?
Yeah, the output resistance is pretty high. And we talked about this a couple lectures back where we actually use a common source output stage. We can also solve that problem. We'll come back and discuss that. What are some other issues with this as an output stage?
Short circuit current.
Yeah, I mean, this again goes back to the bias current, bias point issue, is that really if we bias this thing right at the middle here, and these are pretty large devices, there's going to be a lot of current going through here, right? Because both transistors are on. So the quiescent point, Q point current could be too high. We'll talk about this a little bit more. Okay. Any other issues? Yes, Sang.
It's going to be pretty slow due to Miller capacitance across.
Yeah, potentially speed is an issue, right? So I'll put this in question mark because this is a common source stage. Its intrinsic gain is pretty high, but of course we're going to load it with some resistance. So now our gain, what's the gain of this stage? That's a very simple question, right?
2 GMRL.
Yeah, it's the GM of this device plus the GM of this device multiplied by RL, because these devices are in parallel. So if RL is pretty small, then maybe the gain is not too big. And if the gain isn't too big, then maybe the frequency response. So really we want to make sure the gain is not too high. And hopefully if the gain isn't too large, we can make a good compromise with speed. Okay, so let's talk about how to solve the biasing point problem, first of all. One issue is one way to do it is just to observe that if you consider the curve V in is equal to V out, then this intersects this curve at a pretty good point, right around the trip point of this inverter, right? So one way to bias it would be to have some kind of server loop that takes the output DC voltage and forces the input voltage to be the same. What's a good way to do that? A very simple way of doing that. Okay, Michael?
Yeah, just to resist it between even and.
Yeah, you don't even have to design a loop. You just use some shunt feedback. Alright, because the DC current through the gates is 0, so whatever voltage is at the output, this resistor forces the voltage here to be the same. And in fact, if you don't like this resistor's influence on your circuit, you just make it a large resistor, right? So let's say I'm driving a kilo ohm, and I make this, let's say 10K, 50K. Then effectively it's just a DC. It's only going to affect the DC operation of the circuit. It will not affect the AC operation. So this is actually pretty nice, right? It puts this device into the point where there's gain, right? So if I draw this curve, it exactly puts me at this point here. Again, we know the voltage gain of this is GMN plus GMP times RL, and we again make that relatively low for frequency response. So if I use a large RF, then it only influences DC operating point. But in fact, I don't have to use a large RF. So if I use an RF so that my GM RF is bigger than 1, right? In other words, there's some loop gain in the system, then what happens? What's the benefit of making RF? What's the benefit of making the system have reasonable loop gain? Debo?
You get a lower output impedance also.
Yeah, so if you really let the shunt feedback do what it does best, it can lower the input and output resistance, right? So this lowers input and output resistance. One is good, one is bad, right? Lowering the output resistance is helpful. Lowering the input resistance is not good, because now it becomes more difficult to drive this circuit. It tends to load the stage that's driving it. But it's actually a pretty good solution. One thing that is not so good about this circuit is the biasing. So if I look at the voltage I get VGS-N going from ground to, let's say, this point, and then from this point I get a VGS-P. And that has to equal to VDD, right? So I'm kind of forced to make these VGSs quite large, on the order of half of VDD. And what's the problem with that? I mean, you're making some motions with your fingers.
Swing, output swing.
Yeah, right. So that kind of goes against our output swing. It means that this is a VT plus an overdrive, and I have to make my overdrives large, right? I'm constrained. The other issue is that if these W over Ls are quite large, this is going to take a lot of static power, right? So really what we'd like to do is what we did with our follower class AB stage, is kind of put a battery in here. Because now I can drop some voltage across this battery, and the VGSs of these devices can be set independently of VDD, right? Okay, Debo, you have a comment?
So instead of putting a battery, if we put a, say, capacitor and bias the two devices separately, can that be done?
Yeah, so this battery could be a capacitor, but then the problem with capacitor is leakage, right? So in a switch capacitor system, I could do that, right? I could keep charging up that cap to the right voltage. But if it's a continuous time system, I couldn't do it. And usually if you're driving a resistive load, it's a continuous time system, right? Usually. All right, so the question is, how am I going to implement these batteries? I kind of need a floating voltage source, and that's a little bit hard to do. You know, there's a couple of ways you could do it. In fact, you don't even have to have a floating voltage source, right? Why not just have a couple batteries, a couple of independent batteries, right? Well, the issue is that what I'd really like to do is drive this with a transconductance stage. So I have my transconductance stage, and it would like to drive this output stage. What's the issue? What if I just connect these outputs here and here? What's going to happen?
If it's DC, then the output signal is 0.
Well, let's say AC, right? What's going to happen to the AC signal coming out of here?
To the ground.
Yeah, it's just shorted to ground, right? It's not going to be able to develop a voltage to drive these stages. So, to try something like this, you could say, okay, let me use a follower to buffer this low impedance. So this low impedance, I buffer it with a follower that has reasonable output impedance. This is my output stage. And do the same thing over here. Use another follower. So these voltages plus a VGS gives you the right VGS here. This voltage minus a VGS gives you the right voltage here. And now the output impedance, instead of being very low, it's controlled by how much trickle current you put through here. So now I can drive this with my, let's say, input signal. Can I actually just take the output here and connect it directly here? Would that work? Anybody? Can I take a diff pair or any your favorite transconductor and just drive this output stage as shown? Would that work? Okay, Vincent?
No, because you're going to load the OTA. Because the input impedance is pretty small there for the bias circuit.
Okay, yeah, that's a reasonable point. I hadn't thought of that, but let's say that's not an issue. Let's say that this, I'm getting most of my gain from the other, let's say the first stage, and the second stage can have a reasonably small gain. I just need a gain of 5 or 6. Could you do it?
Don't you have some polarity problems because it's a
Yeah,
positive?
polarity, exactly. So the reason I ask these questions is I like you guys to think about the circuits that we present. I actually shouldn't have even drawn these because this was a big hint. Notice these currents are going in the same direction, right? If I want a class AB stage, as the input voltage increases, I want this device to turn on, this device to turn off, right? So if I drove this with a differential stage, it would actually do the opposite. It would tend to turn both devices on together and both devices off together. So I somehow need to invert this signal and drive this with a signal that has the same polarity. Okay, just a side comment, not that interesting. Well, here's another observation. The other observation is that I've got 2 separate current branches here and here, and all they're doing is biasing up this follower. And so maybe I can actually just get rid of one of them, right? Maybe I can get rid of one extra current branch by just connecting these points together somehow. Because the follower doesn't really care what the drain voltage is too much. And so now I can stop drawing and show you the complete circuit. So this is an output stage. I believe the paper is from this paper. It's probably this paper actually. That's the same, under the same group. But actually, I'll let you guys look at this in the notes. It's probably too hard to read. But there's several output stages. So this original output stage is a CMOS, single supply output stage, using bi-CMOS technology. This paper here is an all CMOS implementation. This one is an implementation with a low voltage source. And finally, this implementation uses something that we'll talk about a little bit later in the lecture. But here's the circuit. So the output stage is, again, common source stages, NMOS and PMOS, class AB. And this circuit actually is very similar to what we just drew. Let's look at how M1 is biased. So M1 is biased through 1 VGS, 2 VGS, minus a VGS. So overall, just 1 VGS. And so if I match this device to this device, by controlling the current in this device, I can control the current in this device. Of course, these 2 devices have to also be matched. So this device is biased up correctly. Let's look at this device. Same thing. I have 1 VGS, 2 VGS, and then down 2 VGSs, and then up a VGS. So this device is also matched to this device, and these 2 devices are also matched. And essentially what I've done here is I've accomplished a couple things. I've produced a voltage between these 2 nodes, right? That's initially what I wanted, was a floating voltage between these 2 nodes. And I can control that voltage by controlling the currents. And I've also produced, as long as I can drive this with the same polarity signal, I can dump a current into both of these nodes and raise this voltage or decrease the voltage, right? If I dump current both voltages go high, this device turns on. If I pull current out, this whole thing drops. This device turns off, this device turns on, and supplies the load current. So this implements our floating voltage supply. Okay? Questions or comments about this?
So basically the input can be kind of single-ended and then split up with two capacitors?
Yeah, you can drive this actually single-endedly. The voltages are different though, so you have to be careful that you take care of the voltages. But if you're more interested in this, I urge you to read these papers. They have a full discussion of all this stuff. Okay, this is just a test circuit that Professor Bozer put together. I didn't have the chance to rerun it myself with our technology node, but it's still interesting to look at this. So has one current source here, and then using an ideal current source, he drives both sides of this circuit, and then he can vary the output voltage and see how that impacts the circuit. And some interesting things come up. So this is basically VGS1 and VGS2 as you vary the input current, and as you would expect, it does the right thing. You can see that for positive currents, this device is turning on. This device is the NMOS device. So the NMOS device is supplying the load here. PMOS device isn't really doing anything, but it's still on, right? We don't want it to turn off because that would introduce distortion. And then as the input current goes negative, the PMOS device does the work. These are the currents of the NMOS and PMOS device. Again, you can see the same information. In this region, this device is supplying the current. In this region, this device is supplying the current. Here you can see the difference between the currents, which is really the output current. And you can see that this has a very nice, nearly linear input-output relationship. As I vary I in, I out varies, and I'm getting a lot of current out of this device. You can see that I can get up to 20 milliamps of current, whereas the quiescent current in the device is quite small, about a milliamp. So this has the nice properties of class AB stage. Notice here the output voltage is 0. Right? So that's the ideal situation. What if the output voltage is offset? Right? If the output voltage is offset, then the symmetry goes away. Right? Now the two devices are biased asymmetrically, and you can see now that linear relationship is gone. You can see on the negative side it's almost the same linear. On the positive side it limits the current. So this really reduces our current drive capability for a bias at the output that's not the optimum bias point. The other issue to look at is how the GM of the circuit varies. So if you plot, because the currents are varying considerably, the transconductances of the output devices are varying a lot. And so what's the issue? Well, the issue is that, you know, if you're swinging a large current, then the GM is changing, which means potentially the stability is changing, right? This is going to produce a pole. At the quiescent point, the pole, let's say, is 10 times your unity gain frequency, so you're not worried about it. But if you put a signal in, all of a sudden the GM of one of the devices drops a lot, its parasitic pole moves closer and potentially produces a stability problems. So you might find that if you put a small step into the circuit, it's stable, but if you put a big step, all of a sudden the circuit is unstable. Well, fortunately, because you have both an NMOS and a PMOS device, the overall GM doesn't vary too much, right? So this is the GM of one device varying more than 2x, but the GM of the sum of the devices varies on the order of, I don't know, 10% or something like that, a little more. So fortunately, having two devices, you don't get as much GM variation. So that actually helps a lot. The other issue to look at is, again, the GM of the device with the output not at mid-rail, right? If you have the output close to one of the rails, then again you get this asymmetric situation. You have to be careful. Now you can see that the sum GM, which is this top curve, is varying a lot. And so again, you can get into an instability region. Okay? So the lesson is that when you design a circuit, just make sure you test it under all the operating conditions. And that's actually, a couple lectures back I said what's really hard about analog design is the biasing. And by that I mean you have to really make sure that your circuit works under all possible bias conditions. All right. There's a couple of other ways of doing output stages that we're going to look at briefly. Instead of using shunt feedback, as we did, we can also use amplifiers in our loop here. And we'll talk about this. This is an error amplifier. It basically takes the output voltage, compares it to the input, and produces an error signal. And so this amplifier is extremely linear. So if you have applications where you really need a linear output stage, this is a very good solution. We'll talk about some of the issues, though, with this. The other approach of designing an output stage is if your output stage, in fact, is producing a pole which is, let's say, significant, it's not it's not beyond the unity gain frequency, then you really have to take it into account. And for instance, you may end up with 3 or 4 gain stages. And so then we'll briefly look at Miller compensation, nested Miller compensation, in order to deal with the multiple poles and zeros that you get in that situation. Okay. So let's first start out with this idea of a helper amplifier. So let's talk about the advantages and disadvantages. So first of all, what are the advantages of the helper amplifier? Well, you guys all know how to read, so I won't ask you. Just like shunt feedback, it lowers your output resistance, right? So what is the output resistance of, let's say, the half circuit? So you have an amplifier of gain A, you have a transistor with output resistance RO. Yeah, RO over A, right? It lowers your output impedance by, in fact, A. As we said, it rejects the distortion, right? Because now my input-output characteristics is extremely linear. How does it do that? Well, this amplifier, in some ways, predistorts these gates so that the overall transfer characteristic is perfectly linear. That's a really nice thing about it. Well, what's nasty about this is the offset voltage. If you build amplifiers, right, they have offset voltages. And now the quiescent current is kind of determined by this offset voltage, right? And this offset voltage is a random variable. So this takes the offset voltage, multiplies it by A, produces a voltage here, which is controlling my quiescent current. Right? That's a bad situation to be in, because if A is large, I can see a huge variation in my output current, my quiescent current, due to these op amps. Okay. So if you are going to design a stage like this, there's some analysis you can do. Look at Gray and Meyer, and you analyze the input-output characteristics as a function of the offset voltage, and you find that if you make the amplifier gain small enough, the circuit probably is going to work okay. But it does produce a pretty big limitation on the gain you can get. So the gain, of course, controls how much lower output resistance you get. So there is a trade-off. There is another solution. I'll just go to that solution in the interest of time. And the other solution is like this. So how does this... Can we zoom in on just the circuit? So how does this help with the... So again, what is this circuit? Well, you'll recognize two circuits in here. I have this circuit, which is nothing but a class AB follower stage, right? So the input voltage just gets followed to the output. M1 and M2 are complementary devices. And then I also connect my input to the circuit that we just looked at. So this is a common source output stage with these helper gain stages. And my output is connected to the output of both. So in effect, this circuit is in parallel with this circuit. So how is this better? Not an obvious question, and so think about it for a while. Well, let's go back. What were the advantages and disadvantages of this stage and this stage? And let's see if the hybrid maybe solves some of these problems. Well, let me remind you, the disadvantage of this was swing. Can't get much swing out of it, right? The advantage of this was swing. So maybe I use this device for small swings and use this device for large swings, right? How does that impact the offset voltage? Well, it's a little bit subtle. What I could do is actually run this device in class AB and run this device in just class B. If I run the second device in class B, then for low inputs it's actually off. It's not even there. And so this offset voltage doesn't even matter. Gain times offset voltage is still not enough to turn this device on. So for small signals, I just have a normal follower. As the signal gets larger, these turn on and deliver the current when the voltage is close to rail. And so then I've solved actually both problems. Of course, it costs me a lot of power, right? I've got two parallel output stages now. But the power is only coming when I need it because I run the second stage in class B mode. Okay, so is there a question?
We couldn't see really well where the input was, if it was at the bottom or in
Okay,
the middle.
let's zoom out. So this is the input coming in here, and you'll notice that the output here is connected to this point. So this is the output. So it's really just a follower. It's just two followers in parallel, two stages in parallel. This is the one stage, right? And this is the other stage.
So bias and VI are just bias voltages, right?
I'm sorry?
The term bias and VI on the bottom stands for bias voltages, to bias up the input stage.
No. You have a good point. Sorry. So, yeah, this is a little bit confusing. So what you'd actually like to do is you could drive this stage from here and drive this stage directly. So you drive them in slightly different ways. But yeah, thanks for pointing that out. That's actually a little bit confusing. So the way it's actually multiple ways of doing this, but the way they've done it is they drive this stage with a regular transistor like we talked about before, and then take the output of this stage and drive, because this is a perfect follower with no gain, then I can take the output of this and drive also this stage. So that's one way of doing it. That's a good question.
So, but to me it's still not clear. So do I use both inputs or do I just use one?
You
or
would
like-
just use one. You would just use one input. Yeah. That makes sense? So you take this, basically, this input here, the way it's been drawn here, this input is the same as this input, right? Because this is just a follower stage. So this is the input signal at this point, right? A voltage here. So if I move this voltage around, this voltage also follows. This voltage is just a level shifted version of this voltage. And I use that to drive the stage. So it's just one input voltage coming in. And here, as drawn, it's using this transconductor to produce that voltage. Okay, so the next topic is nested Miller feedback. And the idea behind nested Miller feedback is, the approach that we've taken up to now is that we want our system to have a dominant pole, and all the other poles have to be bigger than unity gain frequency by design. And we found that if you did end with two-stage amplifier, you had the situation where you had two poles, which were, let's say, comparable, and using Miller feedback, we were able to push one pole to high frequency and push the other pole to lower frequency. And so the idea is, why can't I do that more than one time? So let me just show you what we mean. So here's an amplifier stage. Here's the output stage. Right? Let's say it's a three-stage amplifier. Let's start out with a two-stage amplifier. Right? If this is a two-stage amplifier, this is my second stage. I use Miller feedback around it, and that produces a dominant pole system. Right? So I have a high-frequency pole now and a low-frequency pole. Now I add another stage. Now this third stage is going to produce another dominant pole that's going to be on the order of the dominant pole of this stage. So what I do is I put more Miller feedback around, push this second pole to a higher frequency, push this dominant pole to a lower frequency, and now I could potentially design a system that has three stages and has all the poles and zeros in the right place. Okay? So conceptually, you can see this is a Miller stage, this is a Miller stage. I can even add another stage here and put Miller feedback around it. That's why it's called nested Miller, because you have a Miller feedback stage within another Miller feedback stage. How would you actually implement this? Let's look at a circuit implementation. A little bit messy. Can we zoom in on the circuit? It's messy, but it's actually messy only because you need phase inversion, right? So if I look at this circuit here, to put Miller feedback around here, this cannot be an inverting stage, right? If this were an inverting stage, this would be positive feedback. And because most of our stages are inverting, I'm going to have to use some kind of inverter. So let's start out. This is the input. The input comes here and here. So altogether, this is nothing but a folded cascode, right? So our first stage is a folded cascode. And then this stage here is a common source amplifier, but I mirror the output. And by mirroring the output, I produce a phase inversion. And then again, I have another common source stage, mirror the output, and again, another common source stage. So this is just a bunch of common source. This is a folded cascode followed by a couple of common source stages with phase inversion built in. And of course, you need common mode feedback to make this all work because it's a fully differential amplifier. Well, the way to analyze this circuit, if you look at Gray and Meyer, they analyzed this in quite a bit of detail. And this analysis here is even simpler. And it doesn't give you the exact right answer, but it gives you a good idea. So what we've done here is we've gotten rid of the resistances in each stage. And we just, for simplicity, assume that we just have ideal GM stages with no output resistance. That of course means I have infinite DC gain, right? And a pole at 0. But if I keep in mind that that pole at 0 is actually my dominant pole, which is not quite at 0, I can work backwards and make this work. Okay, so to analyze this circuit, there's the 3 nodes. Write down 3 equations. Make a few simplifying assumptions. First of all, I assume that these Miller caps are much larger than these internal capacitors. I assume that each stage has a reasonable amount of gain, right? The GM RL of each stage. And I just assume the R is so large that I can just neglect it. And again, this is not difficult, but it's tedious. At the end of the day, this is the transfer function you get. And the transfer function, first of all, as you would expect, has infinite DC gain, right? And it has a pole at 0. That's exactly due to what we just talked about, the fact that we got rid of all the resistors. And then it has a couple of poles here. And it has a couple of zeros. Okay? So now to find the poles, I could factor this quadratic exactly, but I'm not going to get any intuition. So again, what I do is I say, well, if I design the circuit right, then one of the poles is going to be much lower frequency than the other, right? Because it's a nested Miller. So again, I use the same dominant pole approximation that we've used before. Can we zoom in on these set of equations? Just this right here. Yeah, thank you. So I factor this out, and I assume that 1 over P2, so this should be P3. 1 over P2 is much bigger than P3, 1 over P3, so that's a dominant term here. And you guys have seen this trick before. That means that P2 is just minus 1 over A1, right, this coefficient. And then P3 I can find because this is the product of the poles. I know one of them, so I solve for the other. And so doing that, this is the solution. That's the DC pole. That's the dominant pole. Of course, it's not at DC. The second pole looks like it's at a pretty high frequency of minus GM over CM2. Remember, CM2 is quite a large capacitance. So again, this is not, you have to be careful. This is not necessarily as high as you might think. And then the third pole, if we simplify it, is first of all the difference between GM3 and GM2, and determined also by the load capacitance. And so of course I want this pole to be in the left half plane, so necessarily GM3 has to be bigger than GM2. Otherwise I get a right half plane pole, unstable system. And if you're nervous about that, right? I mean, if let's say I made this 10% bigger, is that a good idea? Probably not, right? Because over process and temperature, my GMs are going to vary 10%. So what if I just get unlucky and this turns out to be negative? Then I have a right half plane pole. So my yield goes way down. So if you're really concerned about this, you might actually make GM quite a bit larger than GM2, so that over all conceivable situations, it's always larger. So maybe you make it 2 times larger or 5 times larger. So under that approximation, we make GM3 much larger than GM2. And then finally, your unity gain frequency is just determined by the first stage transconductance and the first Miller capacitance. So just as you would expect, this whole thing looks like an amplifier, right? And then it's just a 2-stage amplifier. So all the equations we had for a 2-stage apply. The unity gain frequency of a 2-stage amplifier was the GM of the first stage divided by CM1, right? And now what we've done internally is we've split these 2 poles. So as long as the second pole is above the unity gain frequency, by default, by design, the third pole will also be above the unity gain frequency. Okay, so sounds good. One small wrinkle we have to deal with is the zeros. It turns out that you have a right half plane 0. right? Just as you would expect, right? We had it in a normal miller. We're going to have it here as well. And we have to watch out for the 0, just like we did with the 0 from the two-stage design. Some of the tricks that we use for two-stage could also be used here, right? We could unilateralize the feedback. We could put a follower. We could use cascode devices to try to avoid having a feed-forward path. If we eliminate the feed-forward path, we know we also eliminate the zeros. All the same trade-offs that we discussed before apply here. You put a follower, you reduce the swing. So you have to be careful. In the notes, there are a couple of design examples. I'm not going to go through these examples in detail, but they're just, MathCAD worksheets with some, givens, what we want to achieve, and designs based on these simplified equations. And this is a good starting point if for your project you're planning on doing a nested Miller kind of amplifier design. But these are just starting points. So this gives you a design that then you go into with a simulator and you tweak to get it to work right. Because it turns out that the approximations that we made, right, we forced the poles to be on the real axis. If you're aggressive, you can move the poles off the real axis and make this thing even faster. So that's not necessarily the best solution, to put the poles on the negative real axis. You could split the two higher poles and actually get a little bit of peaking but get faster settling time. So you can play games with this and get pretty good performance. Okay, so that completes the topic of output devices, output stages. We certainly haven't discussed every possible output stage out there. It's a very rich area, but that basically should whet your appetite. If you ever have to do a design of an output stage, you know where to look to get started. Okay, questions or comments? Yes?
So the reason we don't use this inverted type of output stages in BJT, is it for linearity or higher GM? Or?
Well, you do use it, right? The issue with bipolar is that most bipolar stages were designed to drive low impedances, historically, right? And so if you're driving a low impedance, then you really do want to have a low output impedance. And so follower is the choice. For CMOS, usually we're driving either capacitive loads, which we've talked about all through class, or even if you're driving a load, it tends to be a larger load. It's an on-chip load. It's on the order of a kilo ohm, or 10K, in which case you don't necessarily need the low output impedance of a follower. The other issue with the follower is in CMOS is the headroom is not good. The output impedance is not as good as you think, right? The GM is low. The gain is not as good because of the body effect. And so if you look at a simple, straightforward follower output stage in CMOS, there's a lot of issues to deal with. And so you have to do something more fancy. And that's why the combining the common source and common drain is one good option for that. Any other general questions about output stages? Okay, we're going to start a new topic, comparators. All right, so first of all, what do we mean? So there's many situations where you want to detect. I want a circuit that has, let's say, three inputs, or two inputs. Let's say one input is a reference level. The other input is the input signal. And I want the output to be kind of a digital output. In other words, if Vin is bigger than Vref, then the output should be equal to 1. If Vin is less than Vref, the output should be 0. And this is a very useful building block. I mean, at the very simple stage, right, it can detect, let's say, an AM signal, right? If you're, if this is the envelope of an AM signal, then if it's bigger than 0, let's say 0 or some reference, This reference may be something that a feedback circuit has determined the average reference of the signal, average power of the signal. So if it's bigger than some threshold, it's a 1, otherwise it's a 0. It's also a very useful building block if you're building an A to D converter. If I'm building an A to D converter, the world's simplest A to D converter is I compare my input to a whole bunch of references, right? And depending on which ones are bigger, which ones are smaller, I know exactly where my input signal lies, right? That's a brute force A to D converter. It's called a flash A to D converter. I just have a bunch of parallel A to D converters and just observe when the input signal is no longer bigger than the reference. Maybe I'll draw a picture. So this is, let's say, Vref1, this is Vref2, this is Vref3, and my input signal is going to drive all of these. And let's say this is the smallest reference. So if it's bigger than this, I know it's at least this big. And then as I go on, at some point, I'm going to see a shift from lots of 1s to lots of 0s. The top 1 tells me how big my input is, right? Brute force, but it works, and it's very fast because it's as fast as I can make this comparator, right? So can anyone think of a nice circuit that does this? Very simple circuit that will perform this function very nicely. Okay, you want to use the mic?
Differential amplifier.
Sure, differential amplifier. Well, when you say differential amplifier, what do you mean? Do you mean just a diff pair? Well, is the output really a logic level of a diff pair?
I think so. It can go to the VDZ below the VDD.
Let's say I want this to go to VDD and VSS. You're right. But what I'm getting at is, why not just use an op-amp, right? A rail-to-rail op-amp. Right? So rail-to-rail op-amp can swing all the way to VDD and all the way to ground, which is logic compatible. And let's say I put my reference here and my input signal here. Now if the input is larger than the reference, this thing rails, right? It has lots of gain, so it rails. If it's smaller, it rails to VSS, right? So this thing would rail to VIN, to VDD, or VSS, depending on if the input is bigger or smaller than the reference. Any objections to using an op-amp like this? Okay, Michael?
It's maybe too slow. I mean, I can get it fast. I can get it faster because I compensated it, and I don't need to compensate it because I'm not driving it in feedback.
Yeah, excellent point. Let's see how fast this is. Actually, it's interesting to understand. Remember, what's the 3 dB frequency of this thing in open loop? Well, let's first of all discuss a couple of issues. First of all, gain. Do we need high gain? Well, it depends on the application. Let's say I come and tell you I want to resolve a signal as small as a millivolt. Okay? And let's say my supply voltage is a volt. Well, then I need a gain of 1,000, right? So yeah, I may need high gain. If I want to resolve 10 microvolts, I'm going to need more gain, right? So the gain requirements is determined by VDD over Vmin, which is kind of the resolution, right? So the more resolution I want, the higher the gain. Well, I know that if I design an op-amp and I have a certain omega U, right? That's just basically the GM stage divided by either the load capacitance, or if I have an output stage, which I do here, by the compensation capacitance, right? So the 3 dB frequency is omega u over A naught. And if I have an application where I need lots of resolution, then this could be a very low frequency, right? How low? Well, let's take an example. Let's say my omega u is 10 megahertz. And let's say I need a gain of 10,000. So if I divide omega u by A naught, I get 10 mega divided by 10 k, which is 1 kilohertz. That's really slow, right? It's going to take, if you have several time constants to settle, it's going to take several milliseconds for this thing to settle. That's really slow. And these numbers are not unreasonable, right? So Michael's point is you're using a large compensation capacitor because you're going to use feedback. But here, I don't need to use feedback, right? I'm not using feedback. So I could redesign this to be a lot faster.
Why don't you use positive feedback?
We'll talk about that. That's one option. Okay, so that's one issue. It is pretty slow, mainly because we need high gain, and the way we've designed this op-amp was to operate with low gain, and we're using it in high gain mode. So we're actually, it's kind of dumb to go buy an op-amp that was designed for, feedback configuration. If you look at the data sheet of a typical manufacturer, there are op-amps that the manufacturer, that company will sell you, that are just designed for this application. So you don't go and buy the op-amp designed for op-amps for this application. You can actually buy op-amps designed for high-speed applications. What are some of the other issues? I'll give you a hint. If I give a gain of 10,000, does that mean I automatically get 100 microvolts of resolution? Debo?
Limited by the offset voltage?
Yeah. Remember, the way we modeled this is we put an offset voltage in front here. And so now, if this offset were a fixed number, I could just change my reference by the offset. But it's random, right? And all I know is its I know its mean, right? And I know its standard deviation. I know the mean is 0 and the standard deviation is 10 microvolts. Well, that means that I'm going to have to make the signal much bigger than the standard deviation to be sure that I get a certain yield, right? How much bigger? Well, depends on the yield that I want. So if I want a very good yield, the input needs to be at least several times larger than the standard deviation. So if the standard deviation is 10 microvolts, then I can probably use this with 100 microvolt input and be very safe that it's always going to work. So really the resolution is determined by the offset voltage. And actually, it may not be obvious at this point, but in answer to your question, this is why we don't use positive feedback. Because generally an amplifier with positive feedback is going to have a large offset voltage. But we'll come back to that. Alright, so let's look at this figure here. So this figure is kind of the way we're going to design our comparator. We're going to have an input amplifier and we're going to have a latch. Okay, a latch is really what you called positive feedback, and we'll discuss exactly why we use this. First of all, why use a latch at all? What's the purpose of this latch here? Anybody? What are some of the advantages of using a latch? I mean, why do we even have latches?
After we turn off, we still have the state.
Yeah, it's for one thing, it's memory, right? So the input, we sample the input, and then we store the result. So yeah, it's storage. What are some other advantages of a latch?
Maybe like a buffer between the gain stage and your
Yeah, you're right. The latch has gain, so I could actually, if I need gain, I can partition the gain between the input stage and the latch. All right. Any other comments? Why else would I use a latch? Anybody? Well, a latch also not only does it have gain, but also its voltages are by default digital, right? So it can take some small analog voltages and, using its positive feedback, latch them to either the supply or ground, compatible with the digital signaling levels. So it's an interface between the analog comparison and the digital comparison. And then finally, the latch. The nice thing about a latch is that I can design this latch so that on the falling edge of the clock, it clamps the value and it doesn't change anymore. If I always had the input and connected to this digital level could change a lot, right? Just little noise spikes could produce bounces in the output, which could wreak havoc with our digital circuit. So really, for a digital circuit, we need a decision, and even if the decision is wrong, we need it to be consistent, right? For the clock cycle, for everything else to work. So within one clock cycle, the analog circuit says, yeah, I think it's larger. And the digital says, you think? No, it is larger, right? And then all the rest of the digital circuit says, yes, the signal was larger. If you made an error, you're going to deal with it in the digital domain. You don't want this fuzziness, right? The analog never wants to say, well, I think it's larger. No, it is larger. So the latch is kind of like the president of the country, right? These are the advisors. They say, yeah, we think there are nuclear weapons. No, there are nuclear weapons. So just to give you an example. Okay, so what are some of the if you're designing a circuit like this, what are the kinds of things you need? First of all, speed, right? How fast can I clock the system? So that's partly determined by how fast our latch is, and also by how fast this preamplifier is. Offset we already discussed, right? The offset voltage really determines the minimum signal that I can detect. It really determines the resolution. So together, the gain, if I design a good system, my resolution should be determined by the gain, right? At some point, though, if I put too much gain in my system, then I'm overdoing it, because then I'm going to just be limited by offset. And the nice thing about this two-stage design here is that if my latch has a lot of offset, input referred, it gets divided by the gain of this stage. So this is a nice way also to take a latch with a large offset voltage and input refer it. Some other issues which are more subtle. One is overload recovery. So if I'm designing this circuit and I want to clock it fast, I may find that the fact that this latch, if I have internal stages that clamp to VDD or ground, it's going to take me a long time to unclamp the circuit, because unclamping means discharging capacitors, and that's determined by slew rates, right? And so if I don't want to dissipate too much power, then I'm going to have to do something to avoid internal nodes of the circuits clamping too much. The other issue with these kinds is input capacitance, and this is more of an application thing. If I'm just driving one little comparator here, and this has 100 femtofarads of capacitance, I may say, okay, that's fine, I can live with that. But if I'm designing a circuit like that flash converter, and I'm designing, let's say, for a flash converter, the number of comparators you need is exponentially proportional to the resolution you want. So if I want 8 bits, I need 256 of these. So the input capacitance is 256 times larger. And so now I'm really worried about the capacitance loading the circuit that has to drive it. In fact, there's kind of an interesting trade-off there. So in this kind of application, I'm going to take something like a resistor divider string to produce my reference levels. And then I take my input signal and apply it in parallel to all the other stages. So this node sees a lot of capacitance, right? Because it sees all these guys. But maybe that's okay. Maybe I can drive it with a low RS. So if I drive it with a low RS, let's say 50 ohms or something like that, then I won't have too much speed limitation from these input capacitors. Right? Or wrong? Anybody? Does the capacitance problem go away by just making RS small? Well, what about the capacitance over here? Right? I can't make this too small, right? Why not? Current, right? Yeah, I'm going to dissipate a lot of power. So I do care about capacitance because even if I can make my source impedance really small, I'm limited to how small I can make this resistor string, and that may end up being the speed limitation. So here, in this application, I would care about input cap. I also care about common mode rejection. Why is that? Well, my common mode is varying, right? If I go from the bottom to the top, the common mode input is different for each amplifier. And I don't want this to be sensitive to the common mode of the input. I want it to be sensitive to the differential input mode, right? So we want to reject common mode in this circuit. So this is a simple flash converter. And here I have 2 to the n comparisons. Yes?
Just a short question to the RC related stuff. Isn't usually the reference voltage much longer there? I mean, I don't turn it on and off and it's not a signal. So speed is not as much a concern as it would be for the input signal, isn't it?
Yeah, you're right. I mean, these are static voltages, right? But what if, due to kickback, which we haven't talked about yet, what happens is that as these different amplifiers make decisions, there's feedback, capacitor's feedback back onto this node. So you get transient voltages on these nodes. Yeah, I should have mentioned this. Otherwise, it doesn't make sense. These transient voltages on these nodes take an RC time constant to discharge, right? And I want those to disappear as quickly as possible. Otherwise, I'm going to make the wrong decision. Yeah, thanks for bringing that up. Okay, so this is kind of the background to the problem. Here's an example of a comparator that you want to design. Let's say someone wants to design 12-bit ADC running at 100 megasamples per second, and you have a 1 volt full-scale input. Well, your LSB size is 240 microvolts, and the voltage gain that you would need is 1 divided by half your LSB, so about 8,000. So you need lots of gain, and because you're sampling at 100 megahertz, you have to make your decision in 5 nanoseconds. So it's not a trivial design. We'll continue next time.